Good morning, everyone. This is Sajin Fiske from Electrical Engineering Department, SND College of Engineering and Research Center. Today, we are going to start the comparative study of PPI and PID controller for various electrical applications. From that, one of the application is the voltage source inversion, that is fed induction motor drive using PPI and PID controller. Basically, it has to be attempted the present of this comparative study of proportional, that is P, proportional integral, that is PI, and proportional integral derivative controller for speed control of the induction motor. In general, the principle of operating a three-phase induction motor indicate that the speed of the motor is directly related to the frequency of the supply. This fact has made the inverter fed induction motor having a very common configuration in the majority of industrial applications. The VSI fed induction motor drives are increasingly applied in many recent industrial applications that require excellent transit performance of the drive. Better performance of this PPI and PID controller is studied and compared here. So the everyone recognize the vital role played by electrical motors in the development of industrial systems. Induction motors are today a standard for industrial electrical drives, and high performance variable speed drive application have a series of advantages. So there are several ways for the speed control of induction motors fed through VSIs using the different modulation techniques. Basically, most of the researchers or scientists and engineers are continuously inventing the new technologies and methods that covers the speed control requirement of the drive. Advanced control techniques such as fuzzy, neuro-fuzzy, or genetic algorithm, sliding, motor control, etc. have also been extensively used in motion control applications. Inherently, a straightforward operating characteristics, a flexible performance, and efficiency encourage the use of VSI-fed induction motor in many type of industrial drives applications. So most multipurpose efficiency encourage the use of VSI-fed induction motor in many types of industrial drive applications, and production machines benefit from adjustable speed control since the frequently their speed must changes to optimize the machine process or adapt it to various tasks for improved product quality and production speed. VSIs are basically used to regulate the speed of three-phase squirrel cage induction motor by changing the frequency and voltage, and consist of input rectifier, DC links, and output converter. They are available for low voltage range and medium voltage range. The basic action involved in adjustable speed control of induction motor is to apply a variable voltage magnitude and variable frequency to the motor so as to obtain the variable speed of the operation. Both the VSI and CSI are used in adjustable speed etc. So PID controller uses three basic PID types of the modes. A P proportional, I integral, and D is a derivative, while the proportional and integrative modes are also used as a single control modes. A derivative mode is rarely used as its own in control system, and such combinations such as PI and PID controller are very often in practical systems. Then, proportional controller. A P controller system is a type of a linear feedback control system. The P controller system is more complex than on-off control system like a bimetallic domestic thermostat, but simpler than a PID control system used in some time like an automobile cruise control in general, and it can be said that P controller cannot stabilize the higher order process. For the first order process, measuring the process with one energy storage, a large increase in gain can be tolerated. Proportional controller can stabilize only first order unstable process. Changing the controller gain K can change the closed loop dynamic. A large controller gain will result in control system with smaller steady state error, that is better response following, and faster dynamic, that is broader signal frequency band of the closed loop system, and a large sensitivity with respect to measuring noise, smaller amplitude and phase margin. In this controller, see this diagram for P controller. Basically, in this controller algorithm, the controller output is proportional to the error signal, which is the difference between the set point and process variable. In P controller, the actuating signal for the control action in a control system is proportional to the error signal. The error signal is being the difference between the reference input signal and feedback signal obtained from the output. So, for the system considered as shown in this figure, the actuating signal is proportional to the error signal, and therefore the system is called as P controller signal. The error of signal given as follows, as E of t is equal to K of R of t minus H of t, and it is desirable that the control system be underdamped for the point of view of quick response. An underdamped control system exhibit exponentially decaying in the output time response during the transient period. Just wait for a minute. Okay. Now we are moving towards the PI controller. All of you know about the PI controller. We discussed it already in the previous lecture. It means that it is a proportional integral converter. At present, the PI controller is most widely adopted in industrial applications due to its simple structure, easy to design, and low cost. Despite these advantages, the PI controller fails where the controller object is highly nonlinear and uncertain. This PI controller will eliminate the forced oscillations and steady state error resulting in the operation of on-off controller and P controller respectively. However, introducing the integral mode has a negative effect on speed of the response and overall stability of the system. Thus, this PI controller will not increase the speed of the response, but it can be expected since this PI controller does not have mean to predict what will happen when the error in near future. This problem can be solved by introducing the derivative mode, which is ability to predict what will happen with the error in the near future and thus to decrease a reaction time of the controller. These PI controller are very often used in industry, especially when the speed of the response is not an issue. A control without D mode is used when number one, fast response of the system is not required. Secondly, large disturbances and noise are present during the operation of the process. When there is only one energy storage in the process, that is capacitive or inductive. When there are large transfer delays in the system. Therefore, we would like to keep the advantage of the PI controller. This leads to purpose of a PI controller as shown in this figure. And this controller uses the proportional term while the integral term is kept unchanged. The controller output in this case is U of t is equals to K into P into E of t plus K into T into E of t into dt. The block diagram of PI controller is an integral error compensation scheme, but the output response depends in some manner upon the integral of the actuating signal, and this type of compensation is introduced by using controller which produces an output signal consisting of these two terms, one proportional to actuating signal and other proportional to integral. Such a controller is called as proportional plus integral controller or PI controller. Now, the last but one third one is PID controller. So many industries controller employ a proportional integral plus differential and regulator arrangement that can be tailored to optimize a particular control system. That is, PID controller is most commonly used algorithm for the controller design, and it is most widely used controller in industry. The controller used in industries are either PID controller or its improved version. The basic types of PID controller are parallel controller, series controller, and mixed controllers. This PID controller algorithm utilizes or is a design velocity algorithm, and it is also called as incremental algorithm. In the industry, PID controllers are the most common control methodology to use in real application. PID controller has all the necessary dynamics fast reaction on change of the controller input. Increase in controller signal to lead the error towards zero and suitable action inside the control error area to eliminate the oscillation. Derivative mode improves the stability of the system and enables increase in the gain K and decrease integral time constant T1. Which increases the speed of the controller response. These PID controllers are the most often used controller in the process industry. Thus, Majority of the control system in this world are operated PID controller, and it has been reported that the 98% of the control loops in the pulp and paper industries are controlled by a single input, single output PI controller, and that is in the process control application. More than 95% of the controller are of the PID type controller, and this PID controller combines the advantage of proportional, derivative, and integral control action. The control signal is proportional to the error signal and proportional the gain Kp, and here a proportional controller will have the effect of reducing the rise time and will reduce it but never eliminate. If an integrator is added, the control signal is proportional to the integral of the error and the integral gain Ki. So this integral control will have the effect of reduce the error in principle to zero value. The in principle must be added because there are always the limit on accuracy in any system is used to derivative control is used to anticipate the future behavior of the error signal by using corrective actions based on the rate of change in the error signal. The control signal is proportional to the derivative of the error, and Kd is the derivative gain. So this derivative control will have the effect of increasing the stability of the system, reducing the overshoot, and improving the transient response. This derivative control action can never be used alone because this control action is effective only during the transient period. The PID controller make a control loop response faster with less overshoot, and most popular method of control by the great margin. The combined action of this advantage of each of the three individual control actions. Basically, in this diagram, the table 1 and 2 shows the effect of the coefficient and effect of changing the control parameters respectively. As we can there see is a decrease in the rise time, overshoot, and setting time, and there is no change in the steady state error. This PID controller is better than P and PI controller. Now here see the performance comparison of PPI and PID controller. So it is to be noted that when gain is increasing, speed of response is increasing in case of P and PID controller. But in PI controller, the gain of the response is decreasing. In PID controller, there is a minor decrease or no change are shown in various parameters which can be seen from table 1 and table 2, and hence there is no change in steady state error. So PID controller is better than P and PID controller. PI controller. Thank you.